I get asked sometimes about the importance of data structures and algorithms, and my opinion is very clear on these. These are very critical. It really depends why are you learning them. If you're learning them to pass an interview or to get a job, then they are just a burden. You're gonna memorize them. You don't really understand what they do. But if you truly go into these data structure and really look at the root, why they would do they exist and what problems do they solve, they're gonna make you an adept software engineer. You're gonna use this to your advantage, and nobody's gonna bullshit their way through you at all, because you really know when to use this and when to. I'm not gonna talk about development here, coding here, really. I'm talking about actual engineering, working with a database, right? For example, and that's the topic of today, B-trees. We're going to discuss all about the concept of B-trees and how it improve to B+tree, and what is the difference and the advantages, what problems do they solve, what are the limitations of these things. All of this stuff, we're going to discuss it in this episode. Stay tuned. Welcome to the Backend Engineering Show with your host, Hussein Nasser. And guys, if you like these deep dive discussions about database concept, you might enjoy my Introduction to Database Engineering Udemy course. Over 14 hours worth of exclusive content that you won't find anywhere else. So if you're interested, check out the pinned comment below and the show notes as well. If you're listening on the podcast, it really supports the show. Thank you so much. All right, guys. So B-trees. In order to discuss this data structure, why was it invented? We really need to go back into a very real use case. You have a table in a database. It's a huge table, millions and millions of rows, and you want to search for a particular row by its identification. Let's say ID number 1007. You want to look at that ID, okay? And you don't want to really look at that ID for the sake of looking at the value 1007. No, you want to pull more information, right? So you want to get to that row so you can pull more stuff. If you want to search for 70, you already know 70. You're not searching for 70 for the 17. You want more, and that's the key. 17, the value is the tuple. For the longest time, what we do is one by one. Let's read the table page by page. Oh, one page, 1000 rows. Another page, 1000 rows. Read it. Nope. 1007 is not any of them. So you have to read one by one until you find it. And if you're sure that this is unique, so you're going to stop the search, right? And then exit there. This is called a full table scan. You're scanning the entire table, right? And if it's not unique, you know there's more to it, you're going to scan the entire table eventually, which is very slow. Scanning 1 million rows in worst case scenarios, 2 million, 3 million, very, very slow. So it's slow. The trick is, Hussein, make it faster. Make it faster. That's what we want. It's like, how do you make searching 1 million stuff faster? Well, one way is to parallelize it. Let's just split the table in 3, 4, 5, 7, and then let's distribute the jobs on these threads or these machines and let it search. That becomes complicated, but that's one way of doing it. Another way of doing it is to partition it. Partitioning is a very, very important concept. We break the table into chunks based on key sizes. So, okay, values from 1 to 1000 in this partition. Values from 1000 to 2000 is in this partition, on this table. So it's just essentially break it down to multiple tables, right? Another solution we're doing is create an index. So we search on the index, this small data structure, and then once we find it, we jump into the exact page that we need. In all these scenarios and many other scenarios, we always reduce the search space. That is it. We're not doing anything magic, really. If we want, I made a video, so like how to work with a billion row table. Okay, it's exclusive for members on this channel. And the takeaway from that video was, in order to work with a billion row table, you need to avoid working with a billion rows. Yes, it's not really rocket science. Don't search 1 billion rows. Find any sneaky way to avoid working with large data sets. And it's try to segment and eliminate things that you know is not going to give you the results. That's the trick. And here's where this topic is indexes. The indexing, I made a video about indexing, check it out. But the idea of having this index so that I can search only the things that I'm absolutely sure that the row that I'm looking at, the value I'm looking at, is in that space, right? And when you design and structure your index that way, you're gonna get a smaller set. You're gonna search fewer search space, and that the fewer the search space, the smaller the search space, the faster the results. Rocket science, I know. Okay. So, Hussein, how do we build these structures? These trees came into the equation. So, okay, how about we build trees? So how do we build these trees? For the longest time, we had this idea of a binary tree, which is a very, very simple, beautiful structure that says, okay, you put a value on the top, and then larger values go to the right, smaller values of this node go to the left. Very simple data structure. Okay, so if we put a value of 100 here, okay, anything above 100 goes to the right of the tree, right? And I'm doing right here, it's my right, I don't know if it's your right. And anything to the left of the tree is less than 100. So if you're searching for the value of, I don't know, 200, then you always go to the root. So that's one cost, jumping to the root. You say, okay, I'm looking for 200. You know what you're looking at. Is 200 greater or less than 100? This is a cheap check that gives you almost no cost at all. But that check eliminates almost half, if you're lucky, half the search space. Because just like that, you're now searching the right hand side because you know that 200 is going to be in that area. And as a result, you're only going to search 100 and above. So you're searching less results. And this is a very simple example. But the problem with binary tree are by default, they are not really balanced. What does that mean? Take this example. Let's assume the root is 1, okay? And then any value that puts that you add is greater than 1. What will happen? 2, 3, 4, 5, 6, 7. You're going to end up with a linear search space that you didn't really, that is absolutely useless because this is called an unbalanced tree. You're going to end up almost like, if it's not even slower than a full table scan, you're going to jump into multiple pages to get into the value of the 200, but you end up doing more work effectively to search that. So binary trees didn't really satisfy database workload because of this lack of balancing. Okay, so we need a self-healing, self-balancing tree. This is where Btree came into the situation. And Btrees, guys, stands for, really doesn't have it. The paper doesn't really say what it stands for. It could be balanced, could be Boeing, which is the company that the research lab that this paper came from, or could be Bayer, one of the creators of this, the researchers. But yeah, could be anything really. And the beauty of this is it's really truly balanced. So if you think about it, what does really balanced really mean? That means as you insert, the tree balances itself. And if you're an engineer, you must like, oh, wait a second. You're balancing as I'm inserting stuff? The moment you hear that, if you really pay attention, then there's a cost. There's always a cost. And that is where you need to look. So there is a cost on writes, which is this constant rebalancing that needs to happen to balance itself so it's the left is equal to the right. But at the cost of these, as I'm writing, I'm continually balancing my tree, the reads, my reads are gonna be very, very quick as a result. So Btrees are nothing but a generalized binary tree. You can have any number of children, not just 2. You can have 7. You can have 1,000. Really, the database is actually calculate that on the fly. Let's take an example. All right, so this is one of the most popular websites that demonstrates B-trees, and it comes from University of San Francisco. Fantastic website, really. Very simple, right? No fancy stuff, just to the point. So we're gonna explain B-trees here within this website, so effectively. So let's say my B-tree has a maximum number of child. The degree or the order is 3. That means it can have up to 3 nodes. Okay, so let's go ahead and insert a bunch of values. Let's gonna insert a value of 1. So this is gonna become the root, which is 1 here. If I insert the value of 2, right, then when I want to insert the value of 2, we're gonna look, is 2 greater than 1? Well, yes, but I'm not gonna add it as a children because I can actually put the value 2 inside the node itself as an element. Okay, so if I'm gonna insert now, I can have another value. And here's the thing. You might say, Hussein, how many elements or keys can you add in the node itself? It is the value, which is the maximum degree, minus 1, as effectively. It's always like that. So 3 minus 1. So 2 is the maximum you can get. So now if I want to insert 3, what will happen here is, okay, I'm going to insert 3 here, but I'm going to exceed my quota in this node because I'm just exceeded by that. So I'm going to split this node. And that split hurts. That split sometimes really hurts, specifically if you're doing a lot of stuff. The splitting of the page and doing this work, that's all database I/O, right? Think about it this way as I go through this. So if I insert into the value of 3, it's going to insert that. But what will happen is 2 is going to be promoted as root, and 1 is going to be to the left, and 3 is going to be to the right. Let's go ahead and do this. Boom, boom, boom. As we can see, we can this. Now, if I now insert the value of 4, what will happen here? So if I come to here and I say, okay, 4, I'm going to add 4. 4 is greater than 2, so it needed to go to the right of the tree, right? Not to the left. So what will happen here is, as I insert this, it will go to the 4, it will go to the add, and then it will add it as another element in this right tree. And then you can see that now the tree has 3 and 4. Okay, so how do you read this tree? Let's continue reading it. So the value is 2, which is the key here. There is something that is hidden here that is not shown, which is the actual value of that point, the pointer where this value points to. So to the left, we have the value of 1. To the right of the tree, anything that is greater than 2, we have this node. Now you go to this node and you find 3 and 4 are elements in this node. So let's add 5. What will happen? What do you guys think will happen? When you add 5, well, 5 is greater, so it needs to go here, right? And if I add it right here, it's going to go to the node, but we just exceeded the number of elements. It should be just 2. We shouldn't go beyond 2. So now 4 is going to be promoted as a node. 3 is going to go to the left and 5 is going to go to the right. But since we want to keep the levels, 4 are going to be pushed. So we're going to be 2 and 4, and let's add it so we can explain this. Add it. It will get added and then promote that 4. And here's how you read this. Let's read this. This is a little bit different than a binary tree. So this node has the value of element of 2 and element of 4. Okay, the keys 2 and 4. To the left, any values that are less than 2 are here. Any values that are between 2 and 4 are in this pointer. You go here and you search. There could be 1 element, could be 700. Depends on the degree of the tree. And then any values that are greater than 4 goes to the left. So it's a full balanced tree. But look at the work that we're doing as we insert. And tick, 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 tick. We're just balancing and doing all that stuff. And that's because we have a very small element degree of the size, which databases shouldn't use a value of 3. You should have a huge, as big as your page size. All right. So talking about the B trees, let's talk about the benefits of this. If I want to search, let's find value of 3. Very simple, right? Before we go through it, 3, well, 3 is between 2 and 4. First of all, I need to jump to the root and say, okay, where is 3? 3 is between 2 and 4. So I mean, I need to jump to this pointer. So I follow this pointer to whatever node it points me. We are seeing an actual node, but in databases, this is a page. Most of that, at least the Postgres implementation. This is a page itself. This is a page. This is a page. And there's thousands and thousands of elements in that page. Right? So this is an IO. This is an IO. So now I go to 3 and then I found 3. This is a very, very short 3, essentially. And I found it. The value 3, I'm not really interested in the value 3. I'm interested in what is the content of the value 3. And that is the value here. There's something that is not shown in this diagram. I wish they actually showed it, but there is a value. There's not this is not just the tree. We're not looking at just the numbers here. There is some content that associate with the key. It's almost like a key value, right? So the 2 has a value next to it in B-trees. Every element has a value attached to it. So 2 could have any value. Could point, Postgres implementation pointed directly to the tuple ID, right? MySQL implementation pointed directly to the primary key, right? In that case. And that's why if you use a primary key in MySQL that is like a GUID, then your indexes are going to be huge, very huge, right? So be careful what primary key you use in MySQL. Right? In Postgres, they don't have that problem effectively because everything is a secondary key and they always point to the tuple. All right, so that's what we're looking at. So Hussein, why are you telling us that there's values here? Because that is the difference in the other data structure that is called b+tree and what problems it is solved. So now when I'm searching here, this is a page, right? This is a whole page. So if there's 2 and the value of it, whatever that value is, if you're in MySQL, then it's the pointer to the primary key. So the primary key data type goes there. If it's Postgres, it's the tuple. I believe it's, I don't know, 32 bits maybe. Forgot what's the tuple ID value size. So that is the tuple ID in that case. So you put more bits here. So this page is gonna fit fewer elements because we are carrying also values, right? If I only had the keys, I could fit more elements in my page, which is, let's say in Postgres, it's 8K. I can fit more elements there. And as a result, I can search, I can traverse through much more elements in a single IO compared to this data structure, which has the values, which, let's be honest, the values are a burden if you think about it. Another thing here is, what if I am searching for 1, 3, and 5 at the same time? How do I do that? Well, let's search for 1. 1 is here, so I'm gonna read here. Okay, found it. Okay, now I want to search for 3. So let's do it again. Go here and then 3. So you did a double jump to get to the value of 3. Okay, I want to search for 5. Well, let's do it again here. 5. So you did 3 IOs to get to 5. And this is not a great example, but you see that the work you did is like 3 jumps, 3 hops. What if you're reading 100? You're going to go all over the place to find these values because they are, although they are ordered in the tree, but they are not sequential. Once you find a value, it has nothing to do with the value 5, despite them being next to each other in logical view. So now we're looking at a b+tree, and the difference between a b+tree and a b-tree is really just the realization that we're wasting space. We're wasting space by putting the values in next to the key in the elements. It says, okay, what if I don't put the value here? So okay, you have to put the value eventually, right? No, I'm gonna put the values at the leaf nodes only. So now that, well, Hussein, that means you have to duplicate your keys. As we're seeing, the value 3 here also appear at the leaf, but that is a very small cost compared to the benefits that we're getting. All of a sudden now, these intermediate nodes that we're searching are so tiny. We're only searching keys here. They effectively can fit entirely in the memory. So I can traverse this stuff without actually having to worry about the value of them. But once I find something, here's another benefit of a b+tree. Once you find something, there is a pointer to the next actual key. So technically, once you find something, you can find pretty much everything. Range queries in this case in a b+tree are much more effective than in a Btree. Because if I give you, hey, find me all values between 1 and 5. In a Btree, if you go to a Btree, between 1 and 5, you have to search 1. And again, you have to find obviously 2. You have to find 3. You have to have 4. And you have to 5. Because you have to find every one of them, the values itself. Right? So you have to traverse, go back and forth the tree to find this stuff. However, in a b+tree, just go and find 1. We found 1. Once you found 1, just go, because you know everything is sequential, right? If index are always sorted by default. So if it's sorted, then okay, where's the next value? Oh, there's 2. There's a pointer, nice, beautiful pointer. Now you might say, Hussein, isn't the pointer, adding the pointer is a cost? Of course, there's always a cost to everything. So people study and say, okay, the addition of that pointer really doesn't really affect much. But the value of having this beautiful range queries where I can search and then immediately find 2 and 3 and 4 and 5. These might fit into a single page if it's like 5. But let's say you're searching for, I don't know, 2,000 or 3,000, right? You might read, it really depends on, again, on the data size and the values and all that stuff. You might read maybe 3 or 4 pages, right? Depends on the size and all that stuff, right? But yeah, that is the benefits of the difference between Btrees and b+trees. Almost Btrees are never used in databases, right? Although I see some value to the simplicity of the Btree, right? But studies shows that the addition cost of the Btree, which is b+tree, which is the duplication, because you have to duplicate the key itself in the intermediate node and in the leaf node, plus the addition of the pointers to do a linked list at the leaf is almost negligible to the cost of the Btree, right, itself. But if you like, I mean, if you're, for instance, if you absolutely know that your workload is always gonna be, okay, I don't know, key value store, where you're always searching by one value, you're never gonna search by multiple values, then you can use a Btree, right? But I still think that it's very hard. It's harder to fit a Btree in memory fully compared to a b+tree, right? Why? A Btree is you have to put it all or nothing, really. So a Btree is really it's all or nothing. You have to put it all in memory. I mean, you can play tricks with paging. It's like, okay, let's page some part of the tree, but not all of it. But yeah, it's really unpredictable, right? But a b+tree, I'm gonna reference Postgres because that's the database I try to focus on. According to Postgres, when they implemented their b+trees, 99% of the cost and storage of Btrees is in the leaf. This is just 1%. All this nodes that helps the traversor just to get to one leaf is 1%. So definitely you can fit a 1% in memory. Let's say your index is 100 gig. That's a huge index, by the way, if you think about it, right? Then you can fit, if you have enough memory, if you can fit 1 gigabyte in memory, that is fine. Then the traversal are so fast to get to one leaf, and then you're gonna start doing some IO once you get to the actual leaf value, right? And I think I'm still actually thinking about this stuff. Like, is there benefits to using just pure Btree versus b+tree? But always, to me, it looks like always b+tree always wins over Btree. Right, that's what I noticed. I noticed like MongoDB, even being a key value store, they use b+tree. They don't use Btree, and maybe that's actually, let's check. Oh, I take that back. Look at that. MongoDB uses Btree data structure. They did not specify it, said the b+tree. It looks like they are using just a Btree. You know what? I think that's enough. Showing off the screen. Let's discuss this part a little bit. You know, this reminds me of what? It's like this whole thing with MongoDB and just Btree, according to their doc, they're not using b+tree. Okay, they're using a pure Btree. So my guess is they're gonna have trouble fitting that tree completely in memory as a result, because the search, you cannot search through it effectively, right? Just to get to a leaf. It's all or nothing if it's a Btree, because the values are with the keys, so you're burdened with that. That made me remember Discord. Remember the video we did on Discord? Because I remember covering this. MongoDB, the Discord moved from MongoDB to, I believe, Cassandra, and then later they moved to CellaDB because of this exact thing. Let me read this. The messages were stored in a MongoDB collection with a single compound index on channel ID and created app. Around November 2015, we reached 100 million stored messages, and at this time, we started to see the expected issues appearing. The data and the index could no longer fit in RAM, and latency started to become unpredictable. It was time to migrate to database more suited for the task. Again, I'm just putting 2 and 2 together here. My guess is maybe because of the choice MongoDB used a Btree for their indexes, they can't fit the indexes efficiently in RAM compared to if it was a pure b+tree, where you can fit the actual traversal part of things in memory, right? And you can put some of the leaves, which contains the keys and the data itself, right? Which either point to the row, tuple, or the actual value. And if you do that, maybe that was it. That was caused MongoDB to could not fit the Btree structure entirely fully in memory. Because think about it this way: if you can't fit it in memory entirely, then you have to go to the disk. But how do you know what part to put in the disk and what not? You can't have that choice, unfortunately. You have to put, you would decide, okay, I'm gonna put half of it on memory and half of it. But how do you know? You might be unlucky that the queries that needs to traverse the tree are in disk, that you'll end up hitting the disk constantly to retrieve pages just to traverse. Bad stuff. So to me, I still think b+tree is the superior structure, regardless of your really use case, if you think about it. Because like that's what I thought. It's like, okay, I want a simpler data structure. I'm gonna use a beautiful, simple Btree. I don't need a b+tree because it's a key value store. I'm just searching for a key and then give me my value. And that's why was my initial response, as it was in the video, right? Like I started changing my mind while making this video. Then it was like, wait a second. That's fine and all if I have a small index, but what if it's a huge index with a lot of stuff? Then if I can't fit all of this stuff in memory, it's gonna spill to disk, then I'll end up searching all of that stuff in disk. You might argue, Hussein, if your b+tree is so large, I don't know, 1 terabyte, then what is 1% of 1 terabyte? It is 10 gig? Yeah, it's around 10 gig. So I mean, do you have 10 gig worth of RAM? Well, if you're managing 1,000, petabyte worth of content, please invest in a better memory. You should have at least 256 or 512 RAM to fit your 10 gigabit of index. But think about it this way, right? It looks like b+tree always wins regardless. And that's the discussion I wanted to have, guys. It's very interesting. It's like, as I make these videos, I keep remembering old videos that we covered, and we put things and we links together. It's fascinating. I'm going to reference the Discord video that I made, obviously, in the description if you're interested in that stuff. And that's it for me, guys. So what did we discuss? We discussed the beauty of the data structure algorithms. Very important to understand, not memorize for an interview. Actually understand, so it helps you. Once you understand things together, you can put 2 and 2 together and you say, oh, wait a second, this doesn't make sense. And that's where the power of the engineer comes in. Beauty. Then we talked about b-trees and we talked about b+trees and the differences between them, and how do they actually thrive in an actual database production. We've seen an example of MongoDB. Again, that's what they say. They say b+tree. They didn't say b+tree. Regardless, again, I might make another video about b-trees and then how Postgres effectively determine the degree of b-trees. Because if you think about it, it's like Postgres or other database, they don't say, okay, oh, we're gonna use, I don't know, a 2000 degree b-tree. No, they don't do that. They derive that based on your data type of the index you're trying to create. I'm gonna make another video discussing that, hopefully. Stay awesome. Goodbye,